So this talk is going to be a little bit about time series data and specifically getting a point of view on your time series data using similarity, the concept of similarity. And then also what you're going to see is just a little bit about my background, some time series data, kind of examples that I have experienced before. This thing called the matrix profile, what is it? And then how we can use the matrix profile and feed that into a model to help us build. In this case, it's a classification model. And then I'll also take time for some questions. Feel free to also post questions in the Q&A, and I'll try to periodically take a look at them as well. Yeah. So a little bit about me. I know some of it was already mentioned, but I got my master's from the University of Minnesota. I did my bachelor's at the University of Missouri, and essentially been at Target for most of my career. When I first joined Target, I was a data engineer working on their deep learning technologies. So I was able to work on things like getting certain deep learning packages installed, working with data scientists on getting their code to run our large cluster ecosystem. It's a massive Hadoop cluster. And then I also was able to work on our GPU cluster. So I was working on workload management with GPUs, and also getting deep learning code transitioned over to our GPUs from previously some CPUs. And then from there, I joined a team that focused on time series forecasting and anomaly detection. That's where this talk sort of came out of. The work from that team led us to look at something like the matrix profile, look at what research was out there. Can we apply it in certain ways to solve certain problems? And then that's also when I was with that team where I was presenting a variation of this presentation across different platforms. So I presented this in Montreal and San Francisco, and a couple other places as well. And recently, as of middle of COVID, July last year, I joined the AI organization within Target. So I am now a senior AI scientist working under the demand forecasting, I guess you could call it sub-organization. We have multiple sub-teams under there. And then I also, as mentioned before, am the founder and organizer of Data Science Minneapolis. We have over 1,700 members. It was going very well and strong until the pandemic hit and we were forced to switch to everything to Zoom. We did take a break and we were hoping to at some point go back to some type of in-person or hybrid approach, but that's still yet to be determined. So the organizers are talking about that. If you're interested, please reach out as well. Okay, so a little bit about anomaly detection and with time series data. Anomaly detection essentially is just when you, in this case that I'm thinking of, you have time series data, can be anywhere. When I was working on this with Target, we were taking in time series data from anywhere in the company. And the idea was that we would have to build an enterprise system that was able to take a look at your data and alert teams when the data was looking anomalous, because potentially there could be an incident, something went down, something went wrong that could affect our bottom line ultimately. But it was pretty difficult because when you start with a small subset of teams or data that looks very clean, it's very seasonal, it can be a lot easier. But once you start to get a variation, then you start to get, teams that have only been around for a few months and don't have clean data and their systems periodically go down, or data in general by nature, it's very random or sporadic. It gets very, very difficult. And on top of that, even if you have clean data, sometimes it can be a little subjective. So there's no source of actual truth there. So for instance, the data that is typically seasonal clean comes in, it doesn't look like there was an issue. Maybe there's a tiny dip, but statistically it's not actually an issue. Could actually be a big incident. I've seen that before, and you miss it because based on the statistics of it, it didn't look like an actual anomaly or incident. And then vice versa, you could see a little drop in your time series data. statistically you flag it using whatever rules or approach you want, and then it turns out that, oh, it was nothing, it was just something normal. It's just human behavior. So what on that team, what we were using was a very rules-based heavy algorithm. It wasn't extremely scalable. And so it caused us to take a look elsewhere, look at what's out there that we could potentially use. And that's where we came across this thing called the matrix profile. So an example, this is just a made up example I just created using, NumPy and some Python code. So looking at this data on the right, you'll see that over the bottom on the troughs, there's missing data. Well, if you think about it from any retail perspective or any corporation that is dealing with human behavior, at night time, let's say the missing data is at night, you may not receive data. So let's say you're any retailer, you may have, let's say this is some cash register data. Nowadays it's all software based, so you're receiving signals and data from your registers to make sure everything is working smoothly. You can actually sell whatever you are selling. In the middle of the day, everything looks great. You get peaks in the middle of the day, and then once it hits nighttime, everything closes and you're not receiving data. So in this case, this looks normal, right? You're seeing this day after day. In this case, it would actually be anomalous if you started to see data points at night. And so in this case, you have to figure out, okay, how am I going to impute missing data in this case, right? Am I going to do, a mean or zeros? Like, how are you going to approach this? And in this case, you may actually see it in two different ways. Like I mentioned before, if you're expecting missing data at night and there's all of a sudden appears, there's data, this register is on for some reason, it shouldn't be, maybe it's malfunctioning, maybe someone, workers are in the store using it for some reason, or something weird is happening. So you may flag the right portion of this with the data filled in as anomalous. But if it's data that, let's say, same device, maybe you're using a register, but now you're looking at sales. So overnight, you're expecting to get 0 sales and say, it reaches 0. But if you're missing data, then that is anomalous. So the context of which this data is coming from is extremely important. And being able to understand, what this context is without having to actually go and talk to humans and teams and people working the space every single time you have a new data stream coming in, it's impossible to reach that scale, especially in this case, if you're working for a large company, it may be thousands, tens of thousands, I think. And when I was on that team, we were reaching hundreds of thousands of models and forecasts and data streams. So it's impossible to be able to go find out the context on your own manually. Like I mentioned before, in this case, to any user, you may say, oh, the missing data is anomalous. Well, like I mentioned before, if maybe the actual data coming in is anomalous because there shouldn't be any data. So it's very contextual in that sense. So like I mentioned, we had to look at what was out there for anomaly detection. And there was a presentation at a conference. I don't remember which conference. I wasn't actually at the presentation. Someone else on my team was. They found out about this concept and this research called the matrix profile. And it's research out of University of California, Riverside. And initially it was in partnership with also the University of New Mexico from Dr. Eamon Keogh's lab. And essentially what happens is you're taking time series data and creating a distance profile. And this is a little illustration. I'll explain it and break it down so it's a lot more intuitive. If you think about in this diagram or in this picture, on the top, you see a red line. That is your time series data. So that is the data stream coming in that you're wanting to look at and analyze. And on the left, you'll see another time series, the red line. It's a different line. It can be a different one. It can be the same time series. In this case, it is the same. And what it essentially is doing is you're taking a rolling dot product and intuitively you're combing over the time series with this other time series on the other axis. And you're eventually gonna get this, what's called a distance profile. And what then occurs is you look at the nearest neighbor. So you're essentially taking the minimum values and pulling down, and the very bottom, you'll see a white time series right above the link that says where the source is from, cs.ucr.edu. That ends up being the matrix profile. And what how you interpret this is it's essentially a data transformation of time series data, and the peaks are called discords. So the maximum values in this thing called the matrix profile in this white time series down there at the bottom means that in those indices, in those indexes, the max values are actually the most not in similar positions in the time series. So in this case, we could think of them as the maximum values or above a certain threshold could be considered anomalous because they are not very similar to the rest of the time series that it was taking a look at. And on the flip side, vice versa, on the minimum values are essentially in the index where they are the most similar. So if you're looking for time series data to match up where I want to find data that is very similar, then you would look at the minimum values. If you want to look for anomalies or areas that the time series does not look like itself or doesn't look, it looks very different than another time series you're looking at or you care about, then you would look at the maximum values or above a certain threshold. And like I mentioned before, the maximum values are discords. The minimum, the bottom values are actually called motifs. And so if you look into more about the research, you'll see things like motif discovery, discord discovery, and discords calculation. And there are different implementations of this concept with different algorithms that they've come out with more research papers on to determine what the best way to implement this and get it out there. So that is an overview of how the matrix profile works. I know it's a lot to it's a lot of information very quickly. I'll go through it a little bit more and more like an applied aspect of how it works. And from there to essentially what had happened was when we were looking at the research, we also found out that there were no performance necessarily libraries out there in the languages we were running our code in. And so initially at Target, we had implemented a version of the matrix profile library. It then branched off and there were more contributors, more maintainers of the library. So an organization was created that is also in communication with Dr. Iman and the lab. I'm part of that organization. We've had interns from directly the lab that were PhD students. And so they would help write the code and document it and come up with some examples. The current implementation, the most recent one, is under the organization. It's called the Matrix Profile Foundation. It's a Python library. You can download via pip, GitHub. You can contribute. Due to COVID and some other reasons, it's been pretty slow. There's been some people that haven't had the time. We actually had a maintainer for the R library. He's in Portugal, and he, on two fronts, was battling COVID from a research perspective, and also he was a medical professional. So he had to take a break from helping us maintain the repo. So hopefully at some point we can get some more people and efforts into this as well. One quick note too, using a variation or a method of implementing the matrix profile, we were able to calculate the matrix profile in 20 years of data in less than 20 seconds using a NVIDIA GPU, specifically a K80. I remember that actually, I think it was about 17 seconds. So that was pretty fast. I was even surprised that it was that fast. It was a project or just an example. We wanted to show how fast you could potentially get it because that implementation is extremely parallelized, and you can, demonstrate exactly, it calculates almost more of like an approximation, not the exact, but it works pretty well. And getting into that part, like I mentioned, there are multiple implementations and methods of creating what's called a matrix profile. There's many acronyms, there's many papers out there that have different acronyms of how they decide to create it from the same research lab. Stomp is one of the popular implementations, and that's the one that's extremely parallelizable, the one that you can run on a GPU. Scrimp++ is, I believe, an iterative approach versus computing it all at once. So like I mentioned before, the stomp method is what we use for the GPU. It's extremely parallelizable, very fast. Scrimp is a approximation. It's more of an approximation. So you're not calculating the true matrix profile, but you are calculating an approximation of it, which may be good enough for your use case, depending on what that may be. Yeah, and so you can see here there are just different times and seconds and the algorithms in the legend, and you can see that stomp and scrimp were the two fastest. And so a way you can also use this idea of the matrix profiles is to label data. If you're using, in this case, maybe a classification model. So on the top, you see the signal. That is the data. This is just, random made up data as well that we use for examples and documentation. And you can see on the bottom below that we have the matrix profile in the red. You can see that as soon as it gets to in the signal periods of data that look very unfamiliar, the matrix profile spikes up and you get these large values. You can then use this to determine a threshold of in the matrix profile to determine what can we set as like a flag or true 0 1 kind of concept to help you label data if you can't manually go in and label everything yourself. Like I mentioned before with my team at Target a while ago, we would have hundreds of thousands of data streams. It's not feasible to go in and label everything manually. Even if you had a team, we had I think a handful of 5 of us, right? That's not nearly enough people to do something like that. So we had to come up with creative ways, and this was one of the ways we explored, was using something like the matrix profile along with some other rules that we created. Let's label some of our data so that way we don't have to go through it manually, and we get a lot of more training data. And then from there, you can also change the threshold, saying, okay, I want to make something a little bit more sensitive or less sensitive. You could also use this for anomaly detection. You could say, okay, based off just the matrix profile and the raw signal, the time series coming in, I am going to create a threshold, and you can use, any method you really want. We used basic, just, like standard deviations, like outliers. Or looking at max values within a certain window. You can choose whichever one you may want to and use that to label your data and flag anomalous values coming in. The new data stream, as you can see on the very end of the signal and also the very end of the matrix profile, it's starting to go up. If we added more data to the end of that, I'm sure it would go up even more, and you can flag new data coming in as well with this matrix profile and threshold. And so here we can use this data as well for a classification model, like I was mentioning before. So imagine you have your feature set, you have some type of X matrix from X1 to Xn, however many features you may have. Maybe you can also use, in this case, the matrix profile values along with that are essentially showing here with the signal. You can put the matrix profile values in the feature set. So you can have it as a column and show, have a model get a new perspective and learn from, okay, in this case, an anomaly detection model, if the matrix profile values are pretty high, then you may be able to flag and generate a prediction that says that this new data is anomalous, or you can use it on just like a test set, or use it on data you already had that you want to use a model with other features besides just the matrix profile to help you label whether or not data was anomalous. And another just side note about the matrix profile, and something I mentioned earlier, you can also use this to detect where time series are very similar to each other. So in this case, these are 2 time series that I created. They're actually pretty similar, but I shifted them and added noise in certain ways. But if you look at the matrix profile, they're actually pretty similar. What this was an initiative, but we didn't get too far in it because priorities changed. And the idea was that, well, what if we could do this for different time series data within the company? So could we look at data from coming from, one team over here in this place in a company or wherever it may be, and then this data over here coming in, and they're somehow related or correlated, right? So we can take a look at correlation. We can use a matrix profile, and essentially was just going to give us a potential hypothesis that this data may be related to each other in some way. If we know what's related to each other, and in our case, since we're doing anomaly detection, we want to find incidents before they really happen or before they reach an impact to our bottom line, could we find out, if they're related, but also one may be an indicator that something will go wrong in another, right? Or anything along those lines. It was more of a discovery, an idea that we want to explore. And so we were using the matrix profile in that way as well to see if, okay, can we find the matrix profile for multiple time series inputs and then look at where they're very similar to each other. I don't have any results of that because, like I said, I left that team, and the initiative didn't get too far because priorities changed. And back to the modeling approach, if you were to use something like the matrix profile in the modeling approach with a classification model, I used different algorithms, methods to do this, and just to test them out on some sample data I had at work a couple of years ago. And you can see here the different performance of them. At the F-score specifically, you can see that the LSTM network worked. This LSTM network that I created was actually similar to a time series forecasting model I had also created using an LSTM network. They're fairly similar in the architecture. Obviously, I can't show the architecture because that was some IP for a target, but I can say that the matrix profile did increase I think all of these models' performance versus just using raw data and a couple of other features that we were using at the same time. So that was pretty impressive. So what's next? Future state for specifically the library and the organization that is maintaining the libraries. Release a GPU implementation that's been on the roadmap for a little while. The GPU experiment I did to just show, that you can process a lot of data very quickly. That was not a production ready or really a proper method or implementation of it. It was more of looking at what's out there, tweaking things, changing the code a bit, and getting a demo ready to be able to show that this is possible. A lot more development would have been needed and code writing would have been needed, but that's definitely something people have been asking for. I'm not sure if there are any other libraries besides the one I had taken a look at a few years ago that exist now, but as you can see, 20 years and 17 seconds, it can be pretty powerful if a GPU implementation's out there and maintained. And then also multi-series input. So the idea that I can, if you remember this diagram, here we have two time series, right? In this case, it was the same on one axis and the other on the other axis. People are asking, well, can we do multiple time series and compare them against each other? That is something been asked for. It's definitely something that comes up quite often, even to the research lab. There are differing opinions on whether this makes sense to implement or not. I'm not sure if we will get to that. If anyone has any preference or insight onto why this may be extremely valuable versus conducting this on, two time series at the same time and then just doing it multiple times in iterations, feel free to reach out and post some discussions in the repo. But yeah, that's something though that people have been asking about, to be able to look at multiple time series and then calculating a matrix distance profile, and then ultimately the matrix profile across many time series. But yeah, those are the two main asks for this type of work. That's about all I had. There's a link here too to get started with the matrix profile for introductory to be able to look at it from a UI perspective. Feel free to reach out to on LinkedIn or Twitter. I also did want to mention my current team at Target is hiring for 2 senior AI scientists, so essentially the same level as mine and similar position, a little bit different work you'll probably be working on. I posted those links to the Workday, application site to both my LinkedIn and my Twitter. So if you want to apply, feel free to take a look at that and feel free to apply. But yeah, I can take questions. I haven't been looking at the chat or the Q&A, so I guess I can just say them for the end. Let's see. Can the matrix profile library be used for real-time data? So that's how we were using it. So the way we were using it was we were calculating, because the matrix profile actually doesn't take long to calculate, especially it depends on the amount of data you're using for it. So what we ended up doing was we would take a look at the new data points and we'd always have a window. And the window was configurable so you could extend it or shrink it. And when the new data point comes in, you recalculate the whole entire matrix profile and then you set a threshold. And if the new data point was above a threshold, then you can flag as anomalous, and essentially you can keep doing that. And we would do it I remember it was in seconds, but it took like a few milliseconds, if that, to calculate the matrix profile on like 2 weeks of data. So that would have been 2 weeks of data, and that would have been 5-minute aggregation. So I think it would have been 2016 data points, and it would run in a few milliseconds to run that. So it was relatively fast for the use case. The other thing too is we also made the decision that real time in that case, when we're doing anomaly detection alerting teams, the difference between and assuming it's not automated, the difference between like 30 seconds and 15 seconds, or running every 30 seconds, running every 15 seconds, was pretty negligible. So we wanted to run it as much as we could where it made sense, but not too often where no action could have been taken. So for example, if we ran something every 30 seconds and alerted a team, that also may have been too many times, because can they take an action in between those 30 seconds, or can we just, run it every minute, maybe every 5 minutes, right? So what made sense in regards to like, okay, someone actually has to take a manual action, most likely because let's say their server's down, or their containers are down, or something, maybe they have a memory leak or something's going on. It's going to take them a little bit of time to fix it anyway. And as long as they get alerted within, let's say, hopefully a minute or two within that anomalous data coming in, and then they get to go fix it, shortly after. It didn't necessarily make sense to run it, every second or 5 seconds or 10 seconds, because it's just, you would get no added value doing it that often. However, if everything downstream would be automated, then that's when you would start to think about, okay, 5 minutes, minute is too long, because everything can be automated downstream and you want things to recover as fast as possible. So in that case, you would want to start to look at the seconds, if not faster. And that's when you would start to take a look at, okay, maybe there's an iteration. There is, I think it's, what's it called? I think it's either MPX. There's an iterative approach where it's a streaming approach, essentially, where a recent paper or a newer paper from the research lab that developed the matrix profile, they were looking at streaming and iteration. So that way you didn't have to calculate the whole matrix profile. You could just look at the newest data and update the matrix profile. And in that case, if you're looking at automated systems downstream, that would probably be your best approach, is to look at an iterative approach with streaming. I hope that answers your question. Let's see. How much advanced is your used deployed matrix? I'm not sure I understand the question too much. If you could elaborate in the chat, I would love to see that. The deployed in the deployment process in general with this was actually relatively easy. We would do lightweight containers with Docker, and it would just have some Python code in it that would pull data from somewhere on a calendar or on a cycle, and we had a state machine, and it would determine, you know, whether everything's going well. If there was an error, what would happen. We can pause our containers, we can start them up, we can restart them, we could do all of this stuff using an API. And so it was the actual engineering and the architecture wasn't too complex. It was pretty scalable though. It was all Dockerized. The container itself, using the code to do this, the matrix profile work, was very simple actually. It was just not too much Python code. The complexity mainly came in with the rest of the architecture of the system, which was not written in Python. That was actually written in Golang, which worked out pretty well as well. I'm also going to jump to the Q&A so I don't miss people there. Does Stomp work on an NVIDIA A100 GPU? I am not sure. I do not have an A100. I will say that they worked on a K80 and a P100. Those are the only GPUs we had available to us. So I do not know if it will work on anything newer than that. And I mean, you could probably look at implementation of it. I remember there was an implementation that looked at V100s that worked, but you had to edit the code to optimize specifically for a V100 versus like a P100 GPU. So you would have to change the code a little bit to make it work on whatever GPU you are using, because the design of the chips and the GPUs are a little bit different. What precision numbers did we use? We used floating point 32. That was what we were using if I remember correctly, specifically. Is it true that to create the profile, you slide the time series along itself? If you are looking at, if you're comparing the time series to itself to look for things like anomalies or motifs, then yes, but it does not have to be itself. You can compare a time series to any other time series you would like. And then you can essentially say this time series was very similar to this other time series data, and here are the indices that it occurred at, and then you can go take a look at your original time series data to find out, okay, what happened there, and then you go do some investigative work to find out what were the events and the actual causes of the data occurring at that point in time. Let's see, how's it different from calculating autocorrelation function in some way? So, I mean, autocorrelation, yeah, like it's kind of in the name, it's correlation based. I mean, you're taking a look at, you know, the trend, and you're looking at like these data points compared to itself, like across, you know, it's autocorrelation. Like I'm thinking the plots, right? In our, in this case, you know, it's a little bit different. The concept is supposed to be similarity. It's also more along the lines of, like I mentioned, you're looking at comparing it, you know, maybe you can compare it to stuff, you can compare it to any time series that you really want to. So it's just a little bit different. If you want to take a look at autocorrelation to do anomaly detection, I haven't done that. I'd be interested in seeing how you do that, specifically in a case like this, where you're looking at multiple different, and then also looking at something like motifs, where you're looking at, okay, these time series are very similar to the other across different areas of the company and different use in context. So that'd be interesting too as well. And how is this different from shapelets? I'm not as familiar with shapelet. I remember very little about shapelets. I'd have to look it up to give you a definitive answer. If anyone has a link or something to put about shapelets, I can go revisit that. It's been years since I took a look at shapelets. So I'm not as familiar with that right now. Let's see. The matrix deployment to the matrix question again. Are there any use cases of the adapted matrix? I'm not sure what you mean by adapted matrix. Yeah, I'm not sure what you mean exactly by that. And how to reduce the margin of error in this case with the matrix. So in the case of can we reduce the error, if you're talking about the classification model, like I mentioned, I used other features as well on top, like with the matrix profile as just a feature. I think of the matrix profile as more of like a data transformation than anything. So especially when you're inputting that into a model, like I mentioned, all those classification models, I saw them, and I probably should have put that in the plot or in the table, but you pretty much each one of those models and those approaches saw an increase in performance in those metrics when adding the matrix profile data. So it's just another perspective to give the model to learn from the data it's looking at. Oh, sorry. Let's see, I'll go back to chat. How could I compare multiple prior time series records that the same register with the most latest one? So yeah, so you're getting into, it's kind of two approaches there. So you can look at like historical data. So you could say, okay, I want to query, do some type of pooling of data and say, I cared about data last year at this time. And so you look at, okay, I want to pull maybe 2 weeks of data or a week or 4 weeks, whatever maybe. And then you just pull the newest ones that you care about from this year, the most recent ones you want to look at, and you can compare them. It'll basically come over both of them and look at them. And you'll get some type of matrix profile. And then you can see like, okay, there's motifs here. And so there's very similar here, and very unsimilar there. So you can even take a look at this time last year versus this time 2 years ago versus this time 3 years ago, right? Because you're starting to look at, okay, my seasonality too at that point. When you mention multiple time series records, that starts to get into what I was mentioning before, is that people have asked, can I use a multi-series input to calculate matrix profiles? And that's, like I mentioned, kind of up for debate, like there's one maintainer that was essentially asking, how would you really interpret that? How could you get these matrix profile? Like, how many would you want? How many would you need? How many are you going to look at? And then how would you interpret that from like a multi-series input? Was the question, versus something like, oh, I'm going to look at 2 series against each other and then just run that multiple times against different series. And then that at least can get you a little bit better interpretation. It's a little bit more explainable when you're looking at the matrix profile. But yeah, that's something you can take a look at as well. Oh, thank you for posting the link. I should have done that earlier too. Let's see. Should I compare the latest time series against the mean of the prior records? If you're talking about, let's say, like a rolling mean, so you're looking at the mean over time, you're essentially just saying, how is this newest data looking against like the average of how my data used to look like, right? So you're not necessarily saying, okay, I'm going to take a look at this data against how it used to look like, just like raw. You're saying on average how it used to look. How is this raw data going to look? And I don't know what the data would look like, what the data looks like. If the mean is very, if your data is very stable and it's, follows a mean pretty well, then I don't know if there's going to be much difference. If there's a lot of variance in your data in the history, you're taking just the mean, so you're kind of stripping away some information from that. And then comparing it to the current raw data, then you're going to probably see a little bit more like higher values and discords. But at the same time, if you're just comparing 2 data streams together that are the exact same, so let's say you take a mean before and take a mean now, or if your current data looks like the mean as before and it looks the exact same, it's not really useful, because in this concept of matrix profile, you want to look at data that has noise. And so I don't remember if we included it, but there is essentially a discussion we had with the maintainers that if the time series are exactly equal, we should add noise, and it could potentially be a parameter to say, essentially kind of add noise to this data stream, because if they're exactly the same, I mean, you basically don't really get anything out of the matrix profile. I don't even know if it returns anything. It may just return all zeros for all I know, because they're it's identical stream. And if it's all zeros, it's just a straight line, then, there's no noise whatsoever. But yeah, so I would say, especially for that question about taking a look at the mean, it really depends on what that data looks like, but you're losing some information in this case if you strip away a lot of information from the previous historical data. The one thing you should make sure though is that the data is in the same kind of like time buckets and aggregate at the same kind of level with the same methods. Otherwise, or I guess you don't have to, but it depends what your use case is. Let's see. Use cases. Yeah, that one. So. Okay, so mostly about copying out of Zoom. Okay. Let me go back to Q&A. Oh, looks like I answered them. Yeah, so if there are any other questions, feel free. Otherwise, yeah, these are all the slides I had. A lot of great questions. I think someone already posted the link to the repo in the chat as well. Let me also post the link to the papers. I believe it's the link to the papers. Here we go. Okay, I posted a link to the UCR matrix profile site. So if you're interested, I think there's at least like a dozen. There's a new one that's a preprint that came out that Dr. Mankio sent us to that we have an opportunity to take a look at. So the research is still going on. They're doing more and more with this. I know he has some new students coming into his lab. So the work is not, they're obviously still working on this and coming out with iterations of this idea. Yeah, if anyone also, if you've had experience with this, feel free to reach out and, let others know. I've had overall in the applied, world of this, I've had mixed results with it. I found that there are definitely certain data streams that were shown to be successful using the matrix profile as an anomaly detection method and also with the classification method. The classification worked more often because I was using other features. So that's why I like to, think of this a little bit more as a data transformation that you can include into a model. And so that I think worked better than just using the matrix profile straight up as itself and then using that for anomaly detection. But it also depends on, your constraints. If you have a ton of data and a lot of data streams and you can't afford to be able to, train a model, do the whole, feature engineering behind it, cleaning the data and all that, then maybe it will work fine if you just use a matrix profile as is with the raw time series. If you can afford and be able to distribute, machine learning models and deploy them into production, maintain them, and go through the whole process of dealing with that, I definitely recommend taking a look at using this for a model to help you classify or do whatever you may need to do. Yeah. So if there are no other questions, which I do not see any, I can quit sharing my screen and hand it over.
Thank you, Frankie. It was great presentation and it is very engaging. I appreciate your time. I appreciate the audience time. And you guys can also watch this again on YouTube once we edit and release. Thank you.
Thank you. And thank you everyone too for attending.